Students, Pushti sir again. Today I am going to discuss a very important topic in fluids, that is known as buoyant force. So we'll discuss in two parts: when liquid is in equilibrium and when the liquid is accelerating. So this my credentials. So let us discuss what is buoyant force. I have written very clearly, as you see, when an object is submerged in a fluid, the fluid exerts pressure at each point of contact. This you must be knowing on the basics of pressure in a fluid. The force due to this pressure is normal at each point of contact. That also must be knowing. The resultant of this normal pressure force, which is acting at every point of the submerged body surface, is known as buoyant force. Is just renamed as buoyant force. Okay. So buoyant force is not anything, any force that which comes into existence, any separate force. It's just the resultant of the pressure force. Just see this diagram. It's a container containing some liquid, and as you see, I have drawn a boundary here. That boundary is just an imaginary boundary enclosing some part of the same liquid, and this container as well as liquid is in equilibrium. They are not accelerating. The contained liquid is in equilibrium. Obviously, this element of fluid also will be in equilibrium. The whole fluid is in equilibrium. So since it is in equilibrium and the mass of this liquid enclosed within the imaginary boundary is ml. ml is the mass of the liquid enclosed within that imaginary boundary. I have written this here. So from the condition of equilibrium, what are the forces acting on this? One is ml into g due to gravity, and the other forces are the vector sum of this F1, F2, F3, small f. These are the pressure force at each point of the boundary. F1, F2, there will be infinite forces like this. Fn here, because there are infinite points, so there will be infinite small f's. Small f is the pressure force at each point of the boundary. That's what I written here. Normal pressure force at each point of the imaginary boundary is Fi. Okay. Right? So from the condition of equilibrium, the net force on that element should be 0. As you know, that net force on this element should be null. The forces are, one is gravity force ml g bar downward, and the sum of all the small f's. I wrote it very clearly here. From the condition of equilibrium, ml g bar plus sum of fi is null. That is equation 1. So fi, that is the sum of all the pressure forces, the net of pressure forces, is called the buoyant force, as I told you. Fb bar. So ml bar plus fb bar is null, is 0 in magnitude. So fb bar is how much? Minus of ml bar. This is very important observation. Okay, right? So now what you do? Now what you do? Now what you do? You remove this liquid, keep the boundary of this liquid in the container unchanged, but suck out this liquid and replace it with a solid body of same boundary. The solid body of same boundary. Now it is MS. The solid body, solid object of identical boundary. That liquid I removed and replaced with a solid body of identical boundary. So let me write a different color for that. Solid body of identical boundary. Okay. But that means since the outside liquid, the surrounding liquid has remained unchanged. So the small f1, f2, f3, they will remain as before. They will remain as in this figure also. Their values will remain. Understood this? So that's why since the surrounding liquid remains undisturbed, the f1, f2, f3, fn remains same as before. Same as before means in whatever this values f1, f2, fn, the same value will be here also. Understood this? Because the surrounding liquid has remained unchanged. We have not made any changes there. So therefore, the sum of this Fi is the net of the pressure force, which is buoyant force, on the boundary of the solid body remains same as given in equation 3. Equation 3, this is the boundary. This is the buoyant force. That remains same buoyant force here also. How much that is? Minus ml bar. This is very important observation. So the net pressure force on the boundary of the solid body remains same as given in equation 3, which is this. That is on the submerged solid object. This is the buoyant force. So in words we say the buoyant force on the submerged body. So buoyant force, I write it something. The buoyant force on the submerged body okay, the buoyant force on the submerged body is equal to weight of the displaced liquid. This ml is the mass of the liquid which you have displaced out, and in its place you have placed the solid object. So weight of the displaced liquid in the direction opposite to g bar. The minus means minus g bar opposite to g bar. Am I clear? That means the buoyant force on the submerged body is equal to weight of the liquid which has been displaced to accommodate this solid object, and the direction is opposite to g bar. So this you may say, I did not take any cylindrical body and all this. Not required. Any body, I did not, the shape of this body is arbitrary. Okay, this is the best way to prove the buoyant force, evaluate the buoyant force. So this is particularly true for the liquid which is not accelerating. It's an equilibrium case. This is important. If liquid accelerates, then the buoyant force we'll discuss in those cases of the cases of accelerating fluid, we'll discuss in part 2. Okay, so now buoyant force is clear. Buoyant force, in one word, I'll say it is the net pressure force on the submerged surface. Don't think that it is some kind of extra force somewhere coming. It's only pressure force, net pressure force acting on the submerged body in this case. Understood this? But the proof was a very nice proof because we did not assume any shape or size of the body, and this is quite convincing. Am I clear? Now let us see what will happen if the liquid accelerates. That you wait for the part 2 of my discussion. Okay, so thank you all. I'll be coming soon with the part 2. That will be very, very important for you. This is the background, and we call it part 1 of buoyant force. Am I clear? Thank you all. Have a good time. Bye for now.